So on this first one, it's saying that we have a cylindrical container of a fixed radius r is being filled with water. So I'll just draw a cylinder. And the radius of that cylinder is r. Which of the following equations expresses the relationship between the rate of change of the volume V of the water with respect to time and the rate of change of the height with respect to time? So first of all, let's just see, what is this volume? So the volume of something that's like a cylinder, prism, is the area of the base times the height. So the base here is a circle of radius r, so pi r squared times the height h. And so that's an equation for the volume, but that's not what it asks for. It asks for the relationship between the rate of change of the volume and the rate of change of the height. So what I need to do is I need to take the derivative of both sides with respect to time. So here on the left-hand side, that would be dv dt. Now here, when I take the derivative on the right-hand side with respect to time, I have to remember that my r is a fixed radius, so that r is not changing. So in other words, when I take the derivative, I'm just going to treat that r squared as though it were a constant. So it's going to behave the same way that that pi will behave. So a constant times a variable, when I take the derivative, that constant just stays put. So it's just going to be pi r squared, and then the derivative of h with respect to t. So it's just going to be like that. And I think that's one of our options here. So it's this one. All right. So the second problem tells us that f prime of c is 0. So that means that x equals c is a critical point. So if it's a critical point, that means it's a possible max or min of the function. It's a place where the max or min could happen. Then it tells us that the second derivative is negative there. And so if I think about what that means, if this is my f prime and my at c I have 0, and I know that it's concave down there, f is concave down, then that means it's going to be a local maximum, and that is by the second derivative test. So that means that f has a local max at x equals c by the second derivative test. Or in other words, you could say f of c is a local maximum. Okay, so the next one, suppose that the function g of t, and it gives a function there, represents the height of a golf ball above the ground, t seconds since the ball was struck. By solving which of the following equations can we determine the value of t for which the height of the ball above the ground is maximized? And so if I think about this, if this is my function g of t, then if I want to find when the height is maximized, I'm not sure what the graph of g of t looks like. I guess you could plug it into your calculator. It's not really necessary, but anyway, the graph, I did graph it, and it looks something like that. Oops, it's smooth. In other words, I'm looking for this place where it's maximized, and so I know at that maximum, the derivative will be equal to 0. So what I want is to solve is g prime of t equals 0. So what is g prime of t? Well, it's just by the power rule, it's going to be 12t minus, and then if I do 0.75 times 3, that's 2.25 t squared. So g prime of t is equal to 12t minus 2.25 t squared. So I want to set that equal to 0. So let's see, the one that does that is this one here, where I have set the derivative equal to 0. If I solve that, that'll give me the critical points. Okay, so the next one, I'm given the graph of the derivative, And then it says, for what value does f have a local minimum? So I'm going to be, since I know the derivative, I'm going to be using the first derivative test. So I'm going to use this number line here to help organize myself because I think that'll help. So I know that my derivative is equal to 0 at -8, at -4, at 1, and at 4. So -8, -4, 1, and 4. So those places are where my first derivative is equal to 0. And then I want to see if it's positive or negative in between those places. So to the left of -8, I have negative values for my derivative. In between -8 and -4, I again have negative values for my derivative. Between -4 and 1, the values of f prime are positive. Between 1 and 4, the values of f prime are negative. And to the right of 4, the values of f prime are positive. And so what does that mean about the behavior of f? Well, if the derivative is negative, that means f is decreasing. And here again, f is decreasing. And here f is increasing. And here f is decreasing. And here f is increasing. So the question asks, for what values of x does f have a local minimum? And so I can see that at -4, to the left it goes down, and to the right f goes up. So there is a minimum at, so in other words, I can say f of x has a min at x equal -4 by the first derivative test, and again also at 4 by the first derivative test, because I can see that to the left of 4, f is decreasing, and to the right of 4, f is increasing. So those are my answers, so that's B. Okay. On the last one it says, here's my graph of x sine x on the domain -3 to 3. So that's here to here. On the domain -3 to 3. How many values of C appear to satisfy the mean value theorem equation? So for the mean value theorem equation, I want to look at my, so this is telling me that this is my slope of this tangent line that connects -3, f of -3, which is here, and 3, f of 3, which is there. So I'm going to see if I can draw a tangent line there. And then it wants, there's some values of C that are going to have that same slope of the tangent line. So it looks to me like there might be one around here, and then maybe one over here somewhere. But I think that might be the only places where we have points that satisfy that the tangent line is parallel to that secant line. And so I'm going to say that there are 2 such values there.